Not graded in the test. Yep. We're never doing
Got it.
I can't believe you use the same vacancies for us. Like, just be real. No, I didn't grade it. I have a job.
He's a boss himself.
What a sixth grader tells his teacher.
My dog.
I remember when I created it. And I thought it
Yeah, you did really well in that class. Don't feel bad.
this one.
Yes. The highest score was 100%. And the lowest score.
So he won 100%. Possible to get full grade.
What was the cutoff for the A? What percent was it?
Well, there's A and A minus, and I'd say that's around 85%. That would be an A minus. I don't worry about that cutoff so much as I do the cutoff for, say, C to C minus, C to D, and of course D to those cutoffs I pay a little bit more attention
75% would be.
to. A B, a nice solid B. Congratulations.
Not happy.
Do you have that sheet?
No. I apologize. I don't have that sheet.
Do you remember the cutoff for the CED?
I have it recorded, so.
Yeah, it's
Okay.
recorded. I mean, I will when I wake up a little bit more, but it's not quite the moment.
And you don't have your Red Bull today.
I drank it, but it hasn't taken effect yet. Okay. Good morning, everyone. I apologize. I feel like a walking zombie this morning, and I'm not sure exactly why, so. No, I cannot do that. We have to make sure we get over the material, and I kind of need to make sure that I'm here to do it, because apparently when I try to get somebody else to do it, there's a mix-up and they don't, so. All right, we're talking about magnetism. So last time we covered the force of a magnetic field. So now we're going to talk about magnetic flux and magnetic field lines. The only reason why we're talking about that is because it's in this chapter. We usually don't cover magnetic flux until later, but since we already cover electric flux, magnetic flux is not that much different. So we're going to talk about magnetic flux. So if you recall from way back when, Gauss's law, we talked about electric flux. And we used the capital Greek letter phi sub E, which is the electric flux, is the amount of the electric field that penetrates an area. So it's integral over an area of the electric field dotted with that area vector. And recall that the area vector is pointing perpendicular to that area. so that the electric field is uniform and it's at a particular angle to the area vector, then this becomes, so for uniform electric field, this becomes EA times the cosine of the angle between them. And I forgot exactly what variable your text used for that, whether it's phi or theta. So I'll just call it, I'll call it phi. It doesn't matter, okay? What you call it, just that is the angle between the electric field and the area. Okay, well, so magnetic flux. Let's see. So this is the electric flux. Call from before. Now for magnetic flux, we make a little subscript B here because we use B to denote the magnetic field. And so what would it be? Yeah.
Magnetic field times the area.
Yeah. So it's the integral over area of magnetic field dot dA. Cool, huh? So it's just the same exact thing that we did before, except for now we're talking about magnetic field and not electric field. Okay? And in a uniform magnetic field, this would be B A times the cosine of that angle between the magnetic field and the area. Now there's a bit of a difference though between what happens when we do the magnetic flux and Gauss's law for magnetism than we end up with Gauss's law for electricity. So we started out with this definition of electric flux, and then we talked about the electric field lines. And then this will go with the theme of the difference between the magnetism and the electricity. For the electric field lines, they would start at a positive charge and end at a negative charge. So if I were to draw the electric field lines here, they would look like this. So here's the E field lines. And now when we talk about Gauss's law, we talk about closed areas. So enclosed, encased like spheres and things like that. So in this two-dimensional drawing, I'm going to enclose an area, and we're going to look at the electric flux, the amount of the electric field lines that are penetrating that particular area. So notice if I put a closed area here, notice if I put the closed area down here, that's my closed area. Notice that the same amount of electric field lines go into that area as come out of that area. So the total electric flux through this area would be 0. Total electric flux through that area would be 0. This is kind of review, but it's been about 6 weeks, so yeah. I can do this. We could do. So let me draw this dotted area here. So let me draw it so you can move my eyes. So what happens here is that you can see that in this particular closed area, it doesn't work. Okay. If I were to draw this giant area here, okay, notice that that doesn't work. I've got 1, 2, 3 lines going in and 1, 2, 3 coming out. That doesn't work either. It's still 0. So in other words, when we talk about the electric flux through a closed surface, the only way to get it not to be 0 is to include one of the charges. Some type of excess charge must be included. Notice if I just were to put the area over here, surrounding this charge, notice I have 1, 2, 3, 4, 5, 6, 7, 8 lines going in, none coming out. So therefore I get an electric flux through that that's not zero. Okay, so there's an electric flux through there that's not zero. And what it's equal to is, remember,
Q enclosed over something.
something, yes. The something is epsilon naught. The something is epsilon naught, which is the permittivity, electric permit of free space. That big word. Okay. Now let's take a look at the magnetic field and the magnetic field lines and see what happens with it. Now I talked about magnetic field lines before. And so I'm going to expand on my magnet here. I'm going to draw a fatter magnet so I can draw larger magnetic field lines here. So I'm going to draw a fat magnet. We have the north pole over here and the south pole over here. And our lines, as we described before, are loops. They come out of one side into the other and connect back up in the middle. And this would be the way of any magnetic field, whether it be from a bar magnet or any other magnetic field that we're producing. These magnetic field lines are going to be loops, like so. In other words, there's no specific starting point and ending point for these lines. Okay? They go in a loop. Now let's try to draw some Gaussian surfaces for magnetism here. Let's try to draw some. Okay. Aha, here's the other. Okay, so let's use red. I'll use the red ink here. All right, to draw my Gaussian surfaces. Okay, so let's try out here. Okay, so if I try here, what I have is look at this. I've got two lines going in and two lines coming out. So this is my magnetic field lines. So what's the magnetic flux through this surface?
0.
0. Okay. And by the way, even though this drawing is in 2 dimensions and my thing is flat, it would extend to 3 dimensions if this were a sphere. The lines going in would be lines going out. So, and if I started drawing a big bunch of these circles here, let's say I could draw a circle here, like this, right? And I would have, let's see, 1, 2 going in here, 2 going in up here, 1, 2, 3, 4 coming out down here, but they're going in over here and they're coming out over there. It's, you see what I mean? So when I close that surface, so notice I can enclose various surface, I still get zeros. But wait a minute, how did I get that to not be 0 for this? I circle the charge. Okay, so what we can do here is to try and circle one of what? The poles. Let's try to circle a pole and see what happens. So let's circle this north pole. Okay? Now that we've put a dome around Santa at the North Pole, let's see what the magnetic flux is through that dome. Okay? Well, I've got 1, 2, 3, 4 field lines coming out. But I've also got 1, 2, 3, 4 field lines coming in. Because the magnetic field is in a loop, there will not be a beginning and an end. So there's not a starting point and ending point for the magnetic field lines. In other words, we circle the starting point or ending point when we enclose the charge. We circled the place where it started if we close the positive charge. We circled the place where it would end if we enclose the negative charge. But here, there is no beginning and there is no end. There are no magnetic monopoles. Therefore, in the case of magnetism, no matter what you do, no matter how you draw the surface, when you close the surface, it's 0. So if we take a look at the electric field and we ask, are there electric monopoles? Yes. There's an electric monopole. Right there it is. There's a place where the electric field begins. It begins at a charge. Magnetic field, there's none. None. You won't be working many problems with this. That's the idea, theoretical understanding. You need to know the nature of the magnetic field. Loops. So there's your third of the 4 basic equations. We still have to correct the second one, but there's the third one.
What's the second one? BA.
The second one looked like this. So, here, let me write that one's down here. We had this one here. This is the first one. Second one is E dot DL equals 0, and that has to be corrected. That's the one we have to correct. The third one looks like this. Okay? These two are fixed. These two are fixed. Okay? This defines an electric monopole. This is telling you there are no magnetic monopoles. Yes?
You know how you said there's no beginning and no end, but yet you said there's beginning and end at the same time. So if we were to, because you circled the beginning and end in the actual.
No.
So that's
the different fields. The electric field has a beginning and an end.
Yeah, I'm talking about the.
The magnetic field doesn't have a beginning or an end.
That's how it sounded in the beginning. I was like, this one.
No, there is no beginning or no end, because what happens is that yes, it loops outside of here, but it connects back up.
Yeah.
So I could start anywhere on here and go around in
That's what I want to make sure.
right.
You said that
There's no like
at the same
starting
time.
point. There was a starting point that I chose to draw because that's just what I chose to draw. But I could really start it in here and did the same thing. So there's no real point to start. Okay, wow. All right, so takes care of that. All right, now what we're going to do is we're going to just continue on with our idea of charges moving in a magnetic field. And so now what we're going to do is we're going to say we've got a uniform magnetic field. Okay? We're not talking about how we get there yet. We're still not talking about how we get there. And we have a charge moving in it. And we want to look at the nature of what happens to that charge when it moves in a magnetic field. For now, what we're going to do is we're going to take a charge with a velocity that's perpendicular to that magnetic field. So I'm going to draw the magnetic field. This will be a good review of Monday right here. So draw the magnetic field, and my magnetic field goes into the paper. Magnetic field goes into the paper. I have a positive charge. Let's put it down here. It moves, and I will move it to the right with a velocity v. To the right with a velocity v. Okay, so all right, so far now. Now the fun begins. Okay, take a couple of seconds and figure out what direction the force on that charge is going to be. So it's either going to be, because the way I drew it, it's either going to be left, to the right, up the page, down the page, into the page, or out of the page. Those are the 6 possible choices you have for the directions. Okay? So which way do you get? How many of you got to the left? The force is to the left.
Yeah. Wait.
Nobody should have gotten to the left because the force isn't to the left. How many of you got to the right?
Oh, it's your hand goes this way.
Nobody got to the right. Good. How many of you got out of the page? Good. That doesn't work either. Into the page. How many of you got up the page? Yay. Anybody get down the page? If you got down the page, okay, you got up. If you got down the page, you would have been right if that was an electron. If that was something else besides a positive charge. If it's a negative charge, down the page. But for positive charge, up the page.
Oh, the fingers is
Straight fingers in the direction of the velocity. So that when you turn them,
Oh,
they point into the page. Thumb points out. This.
I went the other way around.
A like on Facebook, okay?
Velocity goes right here. It's like this.
All right, so the force is going to move up the page like this. All right, so now let's look at what happens to that velocity. What happens to that velocity? So we want to review a little bit of 220A in terms of what forces do. If I have an object that's moving, let's say that object is moving to the right. Okay, it's moving with a velocity v, and I put a force in the direction of the velocity. If my force is in the direction of the velocity, what's going to happen to this? The velocity will do what? Increase. That velocity will increase because this thing will have the acceleration will be in the direction of the force. Therefore, that velocity is going to increase. Okay? All right, so what happens if I do this? I've got the object moving with the velocity. Second case here is I'm putting a force in the opposite direction of the velocity. What's going to happen to the velocity?
Slow
It will
down.
slow down. All right, it will slow down. So in other words, if the force is in the direction of the velocity, the object will speed up. If the force is in the opposite direction of the velocity will slow down. It will slow down. The speed will decrease. That makes sense, right?
Yeah.
Okay. I mean, hopefully you've experienced this. You know? So we'll talk about the speed here. This speeds up. This slows down. All right, now what happens if I do this? And now I put a force perpendicular to it.
Change the direction.
But that is correct. Okay? You have a force perpendicular to the velocity. Notice with no component, either with the velocity or against it, it will neither speed up or slow down. Will it accelerate? Yes, it will. The acceleration will be perpendicular to the velocity. Acceleration is perpendicular to the velocity, doesn't speed it up, does not slow it down, but it does what? Now say it. I'm looking for you to say it.
It changes the direction.
Yes, that's right. It changes the direction.
Use contour.
Okay? So this changes direction. So if you've got a force perpendicular, it's going to change the direction of motion. It's not going to speed it up or slow it down. It's going to change the direction. So in this case, what happens is that the particle will move. It'll change the direction of motion. It'll still continue to go with the speed v. And it will change in a circle. Obviously, it'll change its direction. When it gets up here, let's say it's moving now this way, along this path. Now, if we notice that this force continues to change direction right along with the velocity, because when the velocity moves, it changes the direction of the force. When we get up to this point in the diagram, notice you go straight up, so that when your fingers turn, they're into the page. Now the force is to the left. Now the force is to the left, so if we draw the force to the left, once again, it's still perpendicular. So this perpendicular motion continues and goes in a circle. So perpendicular velocity in a magnetic field will move in a circle. Move in a circle. So it's a circular motion. With circular motion, we can figure out what that has to be. Back to 220A. The acceleration of an object toward the center of any circle in which it is moving is equal to what is it? Remember? No. Okay, fine. V squared over r, where r is the radius of the circle, v is the speed at which the object is moving.
Is that AC?
That's AC. That's the centripetal acceleration toward the center of the circle, which is moving. So therefore, the sum of the forces toward the center of the circle, toward the center of any circular motion, must be equal to the mass of the object multiplied by this centripetal acceleration, or mv squared over r. Okay, so this is Newton's law for centripetal motion. The sum of the forces toward the center of the circle in which the object is moving is mv squared over r. In 220a, such forces would be friction or tension or whatever's holding the object in a circle or holding the car on the racetrack and allowing it not to slide off to the outside. Notice that if the race car takes the corner too fast and friction is not enough to keep it moving in a circle, it will slide to the outside, crash into the wall, and okay? So now what we got here? Well, we got circular motion. This is circular motion. So we start with the sum of the forces toward the center is equal to mv squared over r. Well, what force is that? That's the magnetic force. Magnetic force. So that is equal to Q V B. Because we're choosing a velocity that is perpendicular to the magnetic field, I'm going to put a little caveat here, and I'm going to say V perp. So V perp. Even though your book doesn't say V perp, it's okay, and so that's equal to m perp over r. And there's one more thing I have to do. Because radii cannot be negative numbers, what we're talking about here is the magnitude of this force. Magnitude is just the sign, is just the number, not including the sign. So we always want to do this to be technically correct about this. In other words, the circle would have the same radius if the charge were negative, except the circle would be in the other direction. It would be in the other direction. Okay, so we can solve for the radius of this. That's one of the things we solve for. And your book is using, your book uses capital R for this, but lowercase r, capital R. Just remember it's the radius of the circle in which the electron is moving, or the proton is moving, or the charged particle is moving. Whatever. So the radius is equal to m divided by q. All right, now there's another quantity that we also will get out of this rather than the radius. So in other words, sometimes we'll measure the radius and we can plug in the numbers and get it. Sometimes we may not know a certain quantity, but we'll know what we talk about. We talk about the angular frequency. If you go back to your rotational motion equations, this velocity is tangent to the circle. So the angular velocity omega, or also what they call the angular frequency. My yellow pen is, it's getting darker, cool. Okay, so omega, your angular frequency, which is equal to the velocity divided by that radius, is Q B over. So in other words, it's just another way to solve for that. But sometimes you'll be given things, your given information will be in terms of this angular frequency. Because you may not necessarily know, what the specific velocity is but you will be able to know like how often it goes back and forth, how often that particle goes back and forth or loops around in the circle. So now this is the charged particle in a magnetic field, the perpendicular part, the parallel part, the parallel part. So what happens if I have a magnetic field, and we actually talked about this last time, magnetic field, and I have a charged particle. Okay, so I've got some charged particle. I'll use a negative sign this time, because it really doesn't matter. Moving with the velocity v. Moving with the velocity v. So what kind of motion do we get for the parallel velocity here? Well, what's the force on this?
Oh, wait. Down.
Zero.
It's 0
Because they're in line.
because it's parallel to it. So the theta is 0, so therefore the force is 0. Okay? If it's going the opposite direction, you can't break your hand to do it. And if it's going in the same direction, it's like, okay, this going this way, this going this way. No matter if I try to turn my fingers, I'm always going to point away from the magnetic field. See, I can't turn my fingers because, you know, when I can't turn them, if I turn them, I'm not going to be turning them in the direction of the magnetic field unless I can turn them that way. I'm trying to turn them that way. It's not working. Okay? So the force here is 0. So if the force is 0 for parallel, motion parallel, force is 0, what kind of motion do you get? Somebody mumbled that magic words. The constant velocity. So parallel motion has constant velocity. Now, we can look at something like this. You see what happens. Okay? So I've got a magnetic field, I've got some velocity at some a skewed angle to this. Some skewed angle to the magnetic field. So in the perpendicular, what kind of motion do you get? Perpendicular. It's a what?
Circle.
Circle. Okay? In the parallel, what kind of motion do you get? Constant velocity. So what you get is you get a circular motion this way. Here's a circle. Oh wait, that's good. So it gets on TV here. There you go. Circular motion. Okay. Now we're going to move it parallel to constant speed. Like that. You get both motions combined. So you spiral. You get a spiral. And spirals along the magnetic field line. I'm not drawing this right. This is what would happen. Yep.
What is it, squiggly thing?
That's a spiral.
No. In the beginning of the spiral.
Oh, that's a V. The velocity is at some angle. It's not perpendicular. It's not parallel. It's got components both directions.
So, at the beginning, how does the forces,
Well, the force is toward the center of the circle, but the thing is going to be moving at a constant velocity.
if you were to draw the force, how do you draw it?
Here?
Yeah.
Oh, well, I mean, because I drew a spiral here, I'm actually would use a 3D perspective thing. So in other words, the force at this point would be, you're going to have fun with this, toward the center of the circle. It moves along, and then the force is still pointed toward the center of the circle. So the force at each of these points is going to be pointed toward the center of the circle in which it is moving at that time. But of course, the circle that is moving is changing as it moves around because the circle itself is moving. So the force is pointed toward the center of the circle.
So I'm wondering,
but the circle itself is moving.
So it's like a line.
Yeah, so here's the center of the circle. So there's the circle center. The force is always pointing toward the circle center, which is moving along with the particle at constant velocity, originally parallel to this magnetic field. Notice it's much different than the electric field. Electric field, the force is Q times E. You have the forces either along the electric field or against it. No matter what you do, if you've got charge, you're going to feel a force in an electric field. Magnetic field, you may not. If you're moving along the magnetic field line, there will be no force. If your charge is not moving, there will be a force. Regardless though, because the force of the magnetic field will always be perpendicular to the velocity of the particle, no kinetic energy is gained from a magnetic field, because the particle will always have that velocity v when it has a motion in the magnetic field. That does not change. In other words, there's an acceleration, but it's always toward the center of the circle. It just makes it go in a circle. No extra kinetic energy is given to that particle. Okay, now we're going to have a set. All right. So now we're going to have a charged particle moving, let's say with some velocity v. And well, I'm just going to say q. I'm going to assume it's positive for simplicity's sake. Positive for simplicity's sake. Okay? It moves into this region. And I have an electric field that points downward. So I have an electric field that points downward. And I have a magnetic field that in this case would point into the page. So I'm going to put a magnetic field into the page. When the charged particle is inside of this region, let's take a look at the forces on it. So let me draw it inside this region. Look at the forces on it. Okay, first of all, the electric force. In which direction will the electric force be? The electric force is equal to charge times the electric field. Since it is a positive charge, the force is going to be in the direction of the electric field. In other words, electric forces, they're either in the direction of the electric field or opposite direction of the electric field. It's a positive charge, therefore the electric force here is going to be in the direction of the electric field. So I'll put an electric force right here. Electric force right here. That says force electric field. It covered up one of the green X's, but that's what it is. Okay? All right, now let's take a look at the magnetic force. The magnetic force, Q, B, cross B. Here we're dealing with the V and the B that are perpendicular, so the cross product in this case will be 1. What direction is that magnetic force? Well, take your straight fingers in the direction of velocity, so that when you turn them, they are into the direction of the magnetic field. Your thumb is pointing up. Okay? So the magnetic force here is up the page. This is magnetic force. So if I looked at the total force on this object, what we have is this would be Q, V, B, because it's in a positive direction, positive y direction, so sum of the forces in the y direction in this case. QVB minus QE. Minus QE. And that's going to equal to
That's it?
no, sum of the forces, and I sum the forces, it's equal to M. Thank you. Don't forget, Newton's law still apply here, all right? So now let's say that the charges of the particles are fixed, and the electric and magnetic fields are fixed, because we start out with those. And we're shooting a big bunch of these charged particles into this machine. Well, notice what happens. Which way the particles will deflect. If we fix the charge, these are fixed, we've set those up ourselves, we're shooting a bunch of these particles in there. Which way they deflect will then depend on what? The thing we don't fix. What's the only thing we didn't fix?
Velocity.
The velocity. So we have various velocities of particles being shot in here. Various ones. Okay? A big bunch of them. They're generated by, I don't know, some radiation interacting with molecules. And we've got a big bunch of particles coming out of there. Okay? We know the charge of them because we know what the reaction is. We know what the nuclear reaction is. So we know what the charge of those particles are. We've set our electric and magnetic fields. And what we don't know is we don't know the velocity. So now, notice if the velocity is low. If the velocity is low, then the magnetic force will be less than the electric force. If the velocity is too slow, then the beam will be deflected downward. Velocity too slow. So, in fact, let me draw another picture here, so without all those x's, so you can kind of see what's going on. So if the velocity is too slow, if the velocity is too slow, the beam will deflect
How slow is slow?
toward the bottom plate. Get there in a minute. If velocity is too fast, goes to stop. Because the magnetic force will be bigger than the electric force. It comes to the top.
So what's the ratio? How do we measure if it's slow, if it's fast?
Well, if we've got some that are slow, the velocity's low, velocity's fast, the electric force is going to be bigger. Well, there's got to be something that is what?
Threshold.
In between, right? Because in other words, if there should be a place where these two forces
Balance
are
out.
equal and cancel each other out. In that case,
So in that case, the electric field is always bigger than magnetic?
Oh, it's a ratio.
not necessarily. It depends on what the velocity of the particles are. Because the magnetic and electric fields are physically different. Okay? But the forces, because one's force depends on the velocity and the other one's doesn't. The other one doesn't. So what happens is there is such a velocity in which the sum of the forces is equal to 0. So let's find out what it is. All you do is take this, and now we're going to set it equal to 0. Set this equal to 0. Notice the charge cancels out here. In other words, it doesn't matter what charge the particles are going in there. It doesn't matter what that is. We can solve for the velocity, and so when the velocity of the particle is equal to E over B, this ratio, the particle will move straight through this region without being deflected either way. Particle will move straight through this region without being deflected in either direction. All we have to do now is block off everything that doesn't go straight through. Block off everything that doesn't go straight through. If we block off everything that doesn't go straight through, when a particle comes out this end, what do we know about it? We know its velocity. We know what its velocity has to be because we've set the electric field, we've set the magnetic field. We know what the velocity of this particle has to be. This device is referred to as a velocity selector. Because we've set the electric field, we've set the magnetic field, we know what velocity we want. We block off everything else that doesn't go straight through, voila. Yes?
Since the forces cancel out, wouldn't the velocity final be the velocity not?
Yeah.
Okay.
Yeah. In other words, the particles enter here, right, with the velocity that they have. Those particles get through will have that same velocity that they come through with. The same velocity. These others would change because they're going to crash into either wall. Oops. Okay. But this one is going to be the same. So in other words, over here, we don't know what the velocity of these particles are. We don't have to know. Sometimes when you use a material to create a beam of particles, the amount of energy it takes for the material, for the, say, electrons you're looking at, to escape that material differs for each electron. And so their velocities when they first come out of the material are going to be different. They're going to be different because we don't know necessarily how much energy it took to get out. So no matter how much energy we put in, they're going to come out maybe with different energies. So they would have different velocities. Well, we want just particular ones because we want to know want to just look at one particular velocity. So what we do is you use a velocity selector. We select only a particular velocity of the beam. Okay? And it could be electrons, could be ions, could be whatever you have. We just don't know their velocities. But when we come out here, we do. Now, the other thing that we can do with this after we know what the velocities are, so we can put this in a combination with the magnetic field on the other side. With just a magnetic field on the other side. So, in other words, what we have is I would attach my velocity selector. I don't want to draw all the X's and lines in here, the velocity selector, but we got a velocity selector. So then when they come out this side, and yeah, well, change the direction of my thing because I drew this down here. So I can have the same magnetic field that I used over here, but I can also use a different one out in this other region. So in this case, I'm going to use a different one. So remember, don't use this magnetic field for this because the magnetic fields could be different. But in this region out here, it enters into another magnetic field. And there's a reason why I drew it up the page. Well, I could draw it in. I don't know, you want to draw it in or I'll draw it in? Sorry. Sorry, guys. Okay? And now what happens is down in this region here, we have a photosensitive plate. This plate is photosensitive. If a charged particle hits on it, it's going to create a flash, a light we have when the charged particle crashes into it. It's going to react, and there's going to be a mark there we can measure. So what happens is that this is going to come out of here, it's going to move in a circle, it's going to loop down here and hit our plate, like that. Ta-da! See it? There's a plate. Now we can measure that distance. we can measure that distance. So if we measure the distance from the opening here to where it hits the plate, what distance would that be? So let's call that that distance right there. What would that be? It would be the diameter of the circle, because once this moves into the magnetic field, it's no longer going to follow the total force of the electric and magnetic field, but just the magnetic force, which is circular motion. So when it gets out here, it's going to be moving in a circular motion. So what we literally measure from this device is the radius of that circle.
What if it's not a perfect circle? What if it's an arc?
This is a semicircle, because you see what we've done is we've put this perpendicular here, so that when it comes out this side and goes directly in the other side, we know that's a semicircle. Because this is here.
So there's no way that it can be an arc. It has to be a semicircle.
Yes, it is an arc, which is a semicircle.
Okay, but I mean not a semicircle arc.
You're talking like
You
more
could-
elliptical.
It depends on, hold on. It's never elliptical.
Okay.
It's never elliptical. Because the particle in the magnetic field will be circular motion.
Okay.
It's circular motion at that point, okay? Let me explain. If I wanted a different part arc of the circle, like a fourth of the circle, I could just put this over here perpendicular to this. In other words, what part of the circle I get depends on how I've set this up. When I set this up with this like this, then notice it's going to be always a half of that circle. If I set it up with my plate over this way, then it would be 1/4 of the circle. So let me show you. Try again. Once you get this visualized, you'll get it. Once you get it visualized, you'll get it. Particles are coming out here with velocity in this direction, okay, perpendicular to that plane, okay, the plane of this. How I set this up, let's say I put my plate here, It's going to circle down and hit the plate. When it hits the plate, it's going to be moving perpendicular to that plate. Therefore, I can tell what part of the circle it is by that particular angle. So in this case, it's 90 degrees, therefore it's a fourth of the circle when I do this. If I've done this, it's 180 degrees, which is half of the circle. Go ahead.
Wouldn't the particle be moving up?
Hold on. I'll get to that.
Okay.
Okay? Let's get to that. Now that everything else is done here. Okay? Okay, first of all, we've measured the radius. So let's write down that formula for the radius here. So we measure this radius. Radius is equal to mv. And the v here, I could just say v because it is perpendicular. So I don't have to worry about that. But just understand that this velocity in the radius is always perpendicular motion. A lot of times you use perpendicular velocities because it's easy. I don't want to skew this thing off, you know, the strength, okay? Over qb, and notice the q is absolute value. When we get to this point, I not only could tell if I measure the radius, okay, I measure the velocity. I know the velocity because I've selected it. I know what the magnetic field is because I've created it. Because I've created that magnetic field. Okay? So what this actually gives me is a ratio of the charge of the particle divided by its mass. The charge of a particle divided by its mass. That's what this will give me. If I know the charge, then I can calculate the mass. So if we know what the charge is, I can then calculate the mass of that particle. Notice, though, the way I drew the circle here. In this case, in the velocity selector, if I put a negative charge here, that reverses each of the two forces. So whether that charge be positive or negative, the velocity is all that matters. So if I just had a beam and I had no idea what the charges were, positive or negative, it would still go straight through. But when you get to this part with just the magnetic field, the direction of the deflection would tell you the sign of the charge. So in this case here, for this particle that I drew, oh, my beam wasn't positive, it was negative. So in other words, this beam would have to be for a negative charge. The reason why I started to draw it out is because I was going to keep the charge positive. But then I realized, oh, well, just change the charge. And, so, and we know the direction of the magnetic field we created. So in this case, this indicates a negative charge. Very good question. It's one of those questions that I would get tripped up on when I say, that's wrong, I can't do it, it's wrong. So I apologize to you for messing you up. So that's a negative charge. There's a very famous experiment which you will end up repeating, except for you don't use a velocity selector. You're going to use an electron beam that is accelerated through a particular potential. I don't know if you've gotten there yet, but it's where you use the, have you gotten to the thing where you use these coils? Yeah. Okay, there you go. You don't use a velocity selector here. What you do is you take your electrons and you accelerate them through a particular voltage. Since you already have the electrons and that voltage is the same, that's where they get their velocity from. So you know what the velocity is. So you always have to know what that velocity is if you're going to try to measure things like this. But the Thompson experiment looked at this number, which we knew before we knew the specific charge of an electron. We knew that number. We knew that ratio before then. Because we could get it from just those beams and those fields. We could get that ratio. But to be specific about exactly what part is the charge here and what part is the coulomb, the specific charge that we got, and then that gave us the specific mass.
But in his experiment, he was trying to hit the charge to the beam of particles, right?
Well, he was trying to figure out what this ratio is, and that's how you do it. Okay, and in other words, and you could test for the velocity because if you use both the electric field and the magnetic field, you try to get it to go in a straight line. But if you notice what happens during that experiment, this is just for those of you in the lab, and those of you not in the lab, you can still glean some good information on this, okay? Because this is important. If you notice, those of you who've done the laboratory where you have the beam and you have the magnetic field and you try to adjust the electric field to make it go straight across. In other words, you're trying to make a velocity selector. That's what you're doing here. When you adjust the electric field so the beam goes straight across, that's what you're doing. But you can never get it to go straight across. You can never get it to go straight across. And there's a reason why. Okay? This is how we try to generate a uniform magnetic field. And those Helmholtz coils are designed in such a way that it's uniform in the middle. But it's the farther away you get from the middle, it's not. Okay? You have these plates, right, to try to generate the uniform electric field. Now, if the plates were what size? If the plates were what size, would I be sure that the electric field is uniform?
Center of the radius of the coil.
No. The electric field. I'm talking about the plates. So remember, how big does a plate have to be?
Infinite.
Infinity. They have to be infinitely large plates. If these plates were infinitely large, right, I could be sure that it would be uniform across. However, these plates, and to get anything readable, the plates, even compared to the distance between them, aren't that great of size. So the electric field isn't quite uniform, but you think, okay, what should be uniform at least across here, but then you've got the edge effects over here. So it's kind of like right in the middle, you actually would have your true EB being uniform in that middle region. But when you get closer to the outside of the measuring thing, it's not. You lose that. And that's why you can never get it to go an exact straight line unless something's broke or something. I don't know. If you turned everything off, it would be, because then it would just go straight with whatever velocity it had in the first place. But once you turn them on to try to figure out the specific velocity, you couldn't really do it because they're not exactly uniform. That's why. By the way, those things are like $1,000.
Yeah.
Please don't pay them. That's like one of the most expensive pieces of equipment. And did anybody get shocked doing this experiment? I actually got shocked once doing this experiment. I forgot. It was a kind of a surprise. I forgot about it. It's like, oh man, I set up the electric field power supply wrong. I forgot to turn it off before going to switch the.
But isn't there?
It was just.
The rubber insulated?
Well, yeah, but I mean, it's still, when I just grabbed it,
Did you wait both hands?
No, just one, but because I'm, it's still, but yeah.
That was 2,000 volts, I guess, right?
Yeah, 5K, yeah. It was fine. Thank God there wasn't that much current. Remember, it's the current will kill you. The voltage won't. I've actually had 1,000,000 volts go through me and didn't even feel it.
What?
Yep, I've had 1,000,000 volts go through me, not even feel it. I was working with a Tesla coil. If you've ever, I wish we had a large Tesla coil. If you've seen it, yes, like the one at the Griffin, where you get the big giant sparks coming out. That thing is at 1,000,000 volts, but it's going at such a high frequency that the electricity just conducts through your skin. And it's such a high frequency, it doesn't mess up your electric system. The reason why the lower frequencies will mess up your electric system is because my heart is trying to beat 60 times a minute. This is going about 60 times a second. It's kind of enough to get it messed up. But if I've got something at a much higher frequency, say 1,000,000 hertz, that's not going to interfere with anything. My heart kind of, no, that's nothing. You know what I mean? My heart, it's too fast. Your heart doesn't get messed up because of it. Your heart won't fibrillate because of that. But if you've got something at a lower frequency, enough that your heart gets mixed up, so higher frequency, lower current, less danger.
It's gonna have a super loud voice that you cannot hear.
Yes. Dog whistles. I remember the last stuff. All right, the last thing we're going to cover, the last part of this, is the moving piece of current in a magnetic field. A piece of current in a magnetic field. So now I have a magnetic field. And I have a piece of current. So I have a wire with a current in it. That wire has a particular length L. And I put that in a magnetic field B. And I want to know what is the magnetic force on that piece of current. Because if I've got a current flowing, that means I've got moving charge. If I've got current flowing, I've got moving charge. Because I have moving charge, there's going to be a force on it. So what you can do is you can kind of do a dimensional analysis, which is the hand-wavy way that I will derive this formula. You can read your textbook for a more formal way of doing it. So the force on the moving charges, remember the magnetic force on a moving charge is Q V cross B. Now if we break this down, the velocity here is dx dt. So all we do is we say, well, let's take the position, the length here, as being some constant, and instead of moving the distance here, we're actually going to move the charge. So in other words, we just kind of switch things up, and we say, okay, so this is Q dx dt. So we switch it when we move to this as the length multiplied by dq dt. Now I'm going to put a vector on the L because charge doesn't have really have a vector. No, we don't have a charge, so keep it. But what is dq dt? Definition from current. That's current. Okay? So what you get is that the force of the magnetic field is the current I, L cross B. And if you want to break it down, the magnitude is ILV sine V, and the direction here is given by the right-hand rule. In this case, your straight fingers go along the current so that when you turn them, you're turning them in the direction of the magnetic field. Your thumb will point in the direction of the force. If we do that in this diagram, straight fingers in the direction of the current so that when you turn it, it is in the direction of the magnetic field. Notice the thumb points in the direction of the force. The difference in this case here and the moving charge cases is we don't have to worry about the charge because the definition of the current is the motion of positive charges. So the force on this. I'm done. Huh? I'll move the paper. So you can see others. And if you want, like I said, the more formal way of doing it, besides just this waving of hands and manipulating units, look at your tab.